Welcome to the deep dive. It's always, well, frankly staggering when you think about figures like Aryabhata, the Aryabhatiya, such a complex system.
It really is. The mathematics, the astronomical models, incredibly advanced for his time, the 5th century.
We've spent time before looking at that mathematical code, the cosmic models he laid out. But, it strikes me that we need to remember these weren't just abstract thoughts pulled out of thin air.
No, definitely not. They were deeply, fundamentally rooted in observation, looking up at the sky night after night, year after year.
Patient, meticulous observation. That's the foundation.
Absolutely right. The kind of precision we see in the Aryabhatiya, the specific numbers for how long planets take to orbit, the exact tilt of the Earth, these weren't guesses.
They had to come from somewhere real.
Exactly. Ancient Indian astronomers, like their counterparts elsewhere, were, in their own way, empirical scientists. They were committed observers trying to make sense of the patterns they saw.
Tracking everything. The sun, moon, planets, stars, day in, day out. Noting when things rose, when they set.
Charting the moon's path, figuring out eclipses. These were major drivers.
Right. So for this deep dive, we thought we'd step back from the pure math for a bit. Ask a really practical question.
A crucial one.
Yeah, what were the actual tools? What technology, what techniques did astronomers like Aryabhata actually have available back then? How did they get the raw data for these revolutionary theories?
How did they see the ancient code in the stars? That's a great way to put it.
Exactly.
And it's so important because when you look at the tools, you start to really appreciate the ingenuity, the sheer dedication it must have taken. I mean, no telescopes, none of the tech we rely on now.
It grounds the genius, doesn't it? Makes it tangible.
It really does.
Okay, so let's start with what the Aryabhatiya actually gives us. We know it provides really specific quantitative information, right?
Oh, incredibly specific. Things like the exact number of revolutions each planet makes in a mahāyuga, that vast cosmic cycle.
Which is what, millions of years?
Billions, actually, in his system. 4.32 billion solar years. And he's giving precise numbers of orbits within that.
Wow. Okay. And things like the Earth's tilt.
Yep, the obliquity of the ecliptic, he gives a value for that. And estimates for the Earth's diameter, the sizes of the moon and sun, their distances, it's all there in the Golapāda section.
Chapters 5 to 7, I think.
That's right. The level of detail, the numerical precision is quite remarkable.
And that precision is the whole point, isn't it? They weren't just saying Mars moves faster than Saturn. They were putting numbers on it.
Exactly. These weren't just qualitative descriptions, they were quantitative values. And to get those numbers, you need measurement, systematic, careful measurement.
So they needed ways to measure angles in the sky.
Angles, yes.
Right.
And track time accurately. And just record things. Record where planets were when eclipses happened over long, long periods.
Right. So the mathematical framework we often focus on, the code.
Mm-hmm.
It wasn't just abstract math. It was designed to handle this data, wasn't it?
Precisely. It was the structure for organizing all those observations, for making predictions based on them, and ultimately for explaining the patterns they saw.
Theory and observation hand in hand.
Inextricably linked. The math gave them the language to interpret the data, to move from just seeing things happen to building models of how they happen.
Okay, so let's get into the nuts and bolts, the tools. What's the most basic fundamental instrument they would have relied on?
Well, probably the most fundamental, used across so many ancient cultures, including India, is the gnomon, the saw.
Śaṅku. Sounds impressive, but it's basically a stick.
Haha. Well, yes. Fundamentally, it's a vertical rod or pillar set up on a perfectly level surface. Simple concept, incredibly powerful tool.
Just a stick in the ground. Okay, I know there's more to it. How does it work? What could they learn from it?
A surprising amount, actually. By carefully watching the shadow it cast as the sun moved across the sky, specifically the shadow's length and its direction, they could figure out some crucial things.
Aryabhata mentions this.
He does. The Golapāda, chapter 3, verse 31, specifically talks about using the gnomon's shadow.
Okay, so the shadow, its length changes throughout the day, obviously. Is there a key moment?
Absolutely. The shortest shadow of the day. That happens at local noon. And the length of that noon shadow, especially on the equinoxes.
When day and night are equal.
Exactly. On those days, the length of the noon shadow has a direct mathematical relationship to your geographical latitude, your Akṣajyā.
Latitude. So how far north or south you are? How?
Well, you measure the shadow length accurately, the height of the gnomon itself, and then it's basic trigonometry. You can calculate the angle of the sun at noon, which relates directly to your latitude.
Using tangents, presumably.
Essentially, yes.
Right.
Or functions closely related to tangents. Aryabhata's sine function, his Jaya, is part of the toolkit needed for these calculations. It's all interconnected.
Wow, so that simple stick gives you your place on Earth, north-south. That's huge.
It's fundamental positional data. Knowing where you are informs how you see the sky. But that's not all.
More.
Direction. The noon shadow, the shortest one, always points exactly north or south, depending on your hemisphere and the time of year relative to the equinox. It defines your local meridian line.
Okay, so it gives you a cardinal direction reference. North-south.
A fundamental axis for all your sky measurements. And of course, just watching the shadow move and change length throughout the day gives you a basic form of timekeeping. A sundial, essentially.
Right. So the gnomon is this bridge, isn't it?
Yeah.
Connecting simple ground measurements to angles in the sky, giving position, direction, and basic time.
A truly foundational tool. It provides that essential north-south anchor for mapping the heavens.
Okay, so gnomon covers direction, latitude, basic daytime tracking. But what about more precise timekeeping, especially for tracking faster movements or things happening at night? Eclipses, planetary positions.
Yeah, for that, you need something more consistent, something that works day and night. That's where the water clock comes in. The Ghaṭī Yantra.
The Ghaṭī Yantra. I've read about these. Bowls with holes.
That's the most common type, yes. You'd have a small bowl, maybe copper, maybe earthenware, with a tiny, carefully calibrated hole drilled in the bottom.
Calibrated being the key word, I imagine.
Oh, absolutely crucial. This small bowl is then floated in a larger vessel filled with water.
And the water leaks in through the little hole?
Slowly, steadily, until the bowl fills up and sinks.
And that sinking marks a unit of time.
Exactly. That marks the passage of 1 Ga, which was standardized as 1/60th of a full day-night cycle.
1/60th. So 24 hours divided by 60, that's 24 minutes.
Roughly,
Yeah.
yes. About 24 minutes in our terms. So you'd need someone dedicated, an attendant, basically.
Watching the bowl.
Watching the bowl, yeah.
Yeah.
Every time it sank, they'd quickly scoop it out, empty it, float it again, and keep a tally, maybe dropping a pebble in a jar or marking a tally sheet.
So you could measure longer periods by counting the guys.
Precisely. You could time how long a certain star took to cross a specific part of the sky, or measure the exact duration of different phases of a lunar eclipse, even at night when the gnomon is useless for time.
That seems vital. Getting actual durations for events, measuring speeds.
Absolutely fundamental. How else do you calculate the orbital periods? How else do you refine those numbers, like the revolutions per mahāyuga we mentioned? You need to quantify how long things take.
So the water clock gives you that consistent temporal measurement, day or night.
It provides that reliable time base, crucial for turning observations into quantitative data needed for the models.
Okay, gnomon for position and direction, water clock for time. What about measuring angles directly in the sky? Like, how high is Jupiter tonight? Or how far apart are Mars and Saturn? The gnomon doesn't really do that, does it?
That's a really important point. No, the gnomon mainly works with the sun's shadow and relates things back to the horizon and the meridian. For measuring altitudes, angles above the horizon, or angular separations between any two celestial objects, you'd likely need different instruments.
And do the texts mention other things? Beyond the Śaṅku and Ghaṭī Yantra?
They do. Various ancient Indian astronomical texts refer to other yantras, other instruments. The descriptions aren't always super detailed, especially in the Aryabhatiya itself, which is more focused on the mathematical models.
So a bit more inference is needed here, looking at the problems they needed to solve and what kinds of tools might have existed.
Exactly. We have to think logically about what measurements were required for their models. It's very likely they used instruments that were, conceptually at least, similar to things like quadrants, or maybe early, simpler forms of astrolabes that we see developing elsewhere, too.
Quadrants, like a quarter circle.
Yes. A graduated arc marked with degrees or some other angular unit, and it would need some kind of sighting mechanism, maybe a pivoting arm, like an alidade with little peepholes or pointers.
Okay, I can picture that. So how would you use it?
Well, to measure altitude, you'd hold the instrument vertically, align the base with the horizon perhaps, and then pivot the sighting arm until you're looking at your target star or planet through the sights.
And then you read the angle off the marked arc.
Precisely. That gives you the angle above the horizon. For angular separation between two objects, you might sight on one, note the reading, then sight on the second, note that reading, and the difference is your angular distance.
Simple in principle, tricky in practice, I bet.
Oh, for sure. But conceptually, that's how you'd get the direct angular measurements needed.
And this kind of data altitudes, separations would be the raw material for mapping the sky, right? For plotting where things are, which you'd need for those epicycle and different models we've discussed before.
Absolutely essential. You can't build geometric models of planetary motion without being able to measure the angles that define those motions. So even if we don't have perfect surviving examples or detailed blueprints from Aryabhata's exact time, the need for such tools is clear, and the texts hint at their existence.
It's important, though, to constantly remind ourselves what they were up against, the limitations. It wasn't easy.
Not at all. We're talking purely naked eye astronomy. No telescopes. That immediately limits you. You can't see faint stars. You can't see moons around other planets. You can't see surface details like craters on the moon or features on Mars.
Just points of light, essentially.
Yep.
And the instruments themselves.
Limited in precision. Think about it.
Yeah.
The accuracy depends on how large the instrument is, how finely the divisions on the arc are marked, how accurately you can actually sight along the alidade.
And the conditions matter too, right? The atmosphere.
Hugely.
Ah.
Haze, dust, shimmering air near the horizon all affect visibility and accuracy. And just the simple physical challenge of holding an instrument steady while sighting a moving target in the dark.
It requires immense skill and patience.
And then there's a time scale. This isn't something you figure out in a few nights.
No, some of these planetary cycles are long. Decades, even centuries, for the outer planets to return to the same spot relative to the stars.
Exactly. So building a really comprehensive, accurate system like the Aryabhatiya implies observations accumulated over very long periods, generations possibly.
Which brings in another challenge: record keeping and knowledge transmission.
A massive challenge. Consistency was key. Careful, systematic recording of observations over years, decades, and then passing that knowledge on accurately without printing presses, without easy duplication. It required a strong tradition, careful copying, rigorous training.
It really paints a picture of a dedicated, continuous scientific effort over a long time.
It absolutely does. The code in the Aryabhatiya wasn't a singular invention out of nowhere. It was built on this long, iterative process.
So let's try and connect those dots explicitly. How does this flow work? From the gnomon shadow and the water clock drips to the mathematical system.
Okay, so imagine this ongoing cycle. You have observers night after night using their gnomons, water clocks, maybe these angle measuring tools, gathering data.
Positions, timings, angles.
Right, a growing data set.
Yeah.
Then that data gets analyzed. People start calculating using the mathematical tools they have, trying to find the patterns, the regularities.
Figuring out the average speeds, the periods.
Exactly. Refining those fundamental parameters. How many revolutions does Jupiter really make in a certain long period? What's the precise ratio of the moon's orbit size to the Earth's size? They use the observations to calculate these numbers.
And those numbers become the parameters embedded in the mathematical models.
Precisely. Those parameters get encoded into the algorithms, the geometrical models, the ancient code of the Aryabhatiya. This model isn't just descriptive, it's predictive.
Ah, so the next step is crucial: testing the predictions.
Absolutely key. The model allows you to calculate where should Mars be next month, when exactly should the next lunar eclipse start and end.
And then you go out and observe again.
You observe again and you compare. Does reality match the prediction? If it does, consistently, over time, well, that builds confidence in your model and your parameters.
But if it doesn't match, if the eclipse is early or Mars isn't quite where the model said it would be,
then you have a problem to solve. It signals that something's not quite right. Maybe the parameters need adjusting based on the new, more accurate data. Maybe the model itself needs refinement.
So later astronomers would take the Aryabhatiya, compare its predictions to their own potentially more accurate observations, and maybe tweak the numbers.
Exactly. It's a continuous feedback loop. Observe, calculate parameters, build model, predict, observe, compare, refine parameters model. That cycle, repeated over generations, is how these systems became so sophisticated and accurate.
That really drives home the scientific nature of it. It's not static dogma. It's a system designed to be tested and improved.
Absolutely. It highlights the incredible skill involved, not just the mathematical insight, but the observational rigor, the dedication to making the models match reality as closely as possible, even with relatively simple tools.
It's quite humbling, really.
It is. It's a testament to their ingenuity, their patience, their dedication, building these predictive systems for the cosmos with just, sticks, water bowls, and maybe some basic sighting devices. It's remarkable.
So if we had to boil it down, the big takeaway here is that the Aryabhatiya's math, its code, wasn't just floating in intellectual space.
Not at all. It was firmly anchored in the practical, messy, challenging work of actually looking at the sky and measuring what was seen.
It shows a culture that really valued both the theoretical abstraction and the empirical data, theory and measurement working together.
Absolutely. It's a powerful reminder that even the most elegant theories ultimately rest on the foundation of observation, of gathering data from the world around us. That link is fundamental to science, then and now.
A really important perspective to keep in mind whenever we discuss these ancient systems. On that note, for our next deep dive, we're planning something pretty exciting.
Oh.
We're going to zoom right into the Aryabhatiya, specifically into the Ghaṭī, the math section. There's a particular algorithm in there.
Ah, I think I know the one you mean. Very clever.
Incredibly clever. It solved a really significant problem for mathematicians and astronomers back then, but what's fascinating is how it resonates, how it connects to mathematical ideas we still use today.
It's one of those beautiful examples of mathematical thinking that transcends time.
Exactly. It really makes you think, doesn't it? How that fundamental drive to observe, to quantify, and to find elegant solutions. It just keeps pushing us forward, from ancient astronomers charting stars to modern science exploring the universe. Something to ponder until next time.
Looking forward to it.